Hi! Within this lecture, we're gonna continue learning about math fundamentals for quantum computing, and we're gonna continue with complex numbers. So maybe you have heard of this term, maybe you have seen this in high school, so let me remind you that we have something called imaginary number. It's actually imaginary because we imagine it because it doesn't exist. So it goes like this: I equals to, or imaginary number equals to square root of -1. Of course, you don't have something like a square root of -1, but it happens that it's actually very beneficial in some kind of complex formulations or complex calculations. And we're gonna do a lot of complex calculations when it comes to quantum computing, and we're gonna deal with geometric linear transformations all the time and matrices as well, and it will be very helpful when we come to there. So complex number is actually any number with combined or added to an imaginary number like a plus bi. B is actually a regular number over here. For example, 5 plus 3i. Okay? And when you see something like square root of -9, for example, you can obviously write that as square root of 9 multiplied by square root of -1, and it's actually equal to 3i. Okay, so bear in mind is that I equals to square root of -1. Again, this is imaginary, we're just using it to be able to do complex calculations. So let's see an example together. We know that I equals to square root of -1, but over here we have something much more complex, square root of I. Of course, this doesn't exist as well, but it may come in handy when we try and do some complex calculations or geometric functions, and we're gonna come across something like that, okay? So square root of I equals to 1 plus I divided by square root of 2. So let's, as an example, prove this. Okay, so how do we get there? Of course, one way to prove this maybe is to take the squares of the both sides of the equation and see if they're actually equal to each other. So maybe you may want to just pause the video here and try for yourselves. Try to take the square of the left hand side and the square of the right hand side and try to see if they are equal. Okay, and by equal I mean if they're going to be equal to I, obviously, because the square root of I, if you just take the square of this, it will be equal to I, right? So pause the video and try to do this on your own. So I hope you managed to do it, but let me show you how it goes. Of course, the left hand side will be equal to I because it's obvious, but over here at the right hand side, we're going to have divided by 2, and we're going to have 1 plus I squared. Now, how do we square this 1 plus I? Of course, this is a squared plus 2ab and b squared. Now, if you just do the calculation, you will just get 1, and then you get 2i, and then you got I squared, right? Because that is the last element over here. But I squared is equal to -1, right? So we get here. So 1 minus 1 will be equal to 0, and 2i divided by 2 will be equal to I itself. So we know this is actually I itself. As you can see, now we proved this. Of course, this is only and one way to prove it, but I believe this will do the work for us right now. So let's go back to our slides, and yep, we've seen this and we have seen this as well. Again, this is only for you to practice, but now we're gonna see how to do summation or like subtraction or multiplication or division by the complex numbers. For example, if you want to add two complex numbers together, you add the regular numbers and then the imaginary numbers by itself, which is very easy, right? So in this case, this is 8, 8 plus 6i, and in the downside over here, we have the 3 minus 2i and minus 5 plus 4i. Of course, we're gonna deal with 3 minus 5 and then 4i minus 2i. So just add the real numbers by themselves and the imaginary numbers by themselves. Of course, it goes the same way for the subtraction as well. If you're gonna do a multiplication, then you're gonna just have to multiply the real number and then multiply the imaginary number. That's it. It's very easy, and it goes the same way for dividing a complex number as well. You just divide the real number and then you just divide the imaginary number as well. So this is easy, right? However, there can be some other alterations over here when we try to actually work with the complex numbers. For example, if I want to just multiply a complex number by an imaginary number, it's not going to change much, right? Because we're just going to multiply by the real number and then just the imaginary number as well. However, yeah, I forgot to add 2 over here. However, this time, this will become 3i plus 2i squared. And it means that 2i squared will be minus 2, right? Because I squared will be minus 1. So here you go. Now we have minus 2 plus 3i. And again, if you want to do this thing, 5 plus 3i, 3 plus 2i, then you're gonna just follow the same exact thing that you should do when you do with a real number. So this will be 9i plus 6i squared. And this will be, of course, 15, 19i and plus 6i squared. And maybe you already understood that 6i squared will be actually minus 6, so that you get to plus 9 plus 19i. Okay, so as you can see, when we multiply complex number with a complex number, just beware that when you see I squared, just put minus 1 instead of it. So there's a term called complex conjugate, and it is actually related with the complex numbers. So if you see something like complex conjugate of some complex number, it means that you're gonna have to change the sign of the imaginary part. Okay, not the real part, only the imaginary part. So as you can see, if it's a plus, you're gonna do it as a minus. If it's a minus, you're gonna just convert it into a plus. We're gonna use this complex conjugate a lot in the quantum computations, as well as we're gonna use the squared magnitude as well. So squared magnitude means only you're just dealing with the real numbers and just take the squares of it. But don't forget about it. Complex conjugate, you're changing the sign, okay, sign of the imaginary part, not the real part itself, only the imaginary part. And in the squared magnitude, you're only dealing with the coefficients of the real number, of course, and also the imaginary part as well. We're not dealing with the I itself, we're only dealing with the coefficients of it. So 3 squared and 2 squared in this case. Okay, we're gonna use this a lot in the actual probability calculations when it comes to quantum computing as well later on. So these are all terms you may get confused around here, or you may want to take notes. Feel free to do that, or you can just come back to the slides. I'm going to share all the slides with you at the end of the course, so don't worry about it, okay, if you don't want to take the note. But these are all terms you just have to memorize in some part of the way. So complex number multiplied by complex conjugate of that number is actually the squared magnitude of that number. So how do you do that? just take this as an example. 3 plus 2i, and the complex conjugate of it, of course, will be 3 minus 2i. If you multiply them together, let's see what you get. Maybe you may want to pause the video and just do it yourselves in order to understand that this will be squared magnitude. So I'm going to do it. 9 minus 6i and plus 6i, and then you're going to have minus 4i squared, right? So minus 6i and plus 6i will be canceling out each other, and we're going to have like 9 plus 4, right? Because I squared will be minus 1 eventually, so we're going to have 9 plus 4. And this is exactly the definition of the squared magnitude, right? Again, we're going to have a lot of examples regarding to this kind of operation, but just so you know, just try to memorize at least the terms: complex conjugate, squared magnitudes. Okay, that's it for the complex conjugate and squared magnitudes, but we're going to learn something related with the division of the two complex numbers. Now, it's easy when you try to divide a complex number by a real number, but it can get complex when you try to divide a complex number to complex number. So I here have a very easy actually division, because you can easily see that the upper part is actually the 2 times of the lower part. But if it wasn't, then we're gonna have to just multiply the whole thing with the complex conjugate of the dividing part. Okay, so over here we have seen that if we want to actually divide the complex number by a real number, it's very easy. You just divide the a real number and then the imaginary number. By doing so, I know that by multiplying this with the complex conjugate of itself, I know that it's going to result in a real number, right? Because it's going to result in the squared magnitude of that imaginary part, or the complex number itself. So I'm going to do exactly the same thing that I have done over here. So I'm going to multiply it by 3 minus 2, 1. Of course, not to just make things wrong, I'm going to multiply the upper side as well. It will result in 13. But what about the upper part? Of course, I'm just going to multiply these two together, and eventually it will come out as 18 minus 12i plus 12i, and then minus 8i squared. And if we do the calculation, it will be 26 divided by 13, and it will be equal to 2. However, again, this doesn't have to be necessarily a real number if we divide them together. If we have a regular number at the dividing part, then we can just write it as like a plus bi divided by something. Okay, the trick over here is to just take the complex conjugate of the denominator and just multiply the whole complex division by the complex conjugate. Great. Now, I believe we have seen enough for the complex numbers, and you have all of those things in your slides. Okay, we're gonna stop here and we're gonna continue with the matrices, which is the one of the most important parts that we're going to be seeing during this section. See you in next lecture.